everybody. This is Odo. This is one of Eric's cats, and he's sort of like a company's mascot, and we want to present him to Todd Resudek because Todd has been an incredible guest host on Elixir Wizards now multiple times, 3 times now, and we just really appreciate the work that you've done with us on the podcast, and thank you very much, Todd. Todd is also one of the Elixir community's, I call him everybody's best friend. He's just a really nice person, and everybody loves Todd, and he's a contributor to Hex. He's about to give us a talk on nerves. So everybody give it up for Todd Resudek.
Thank you, Justice. To be fair, Eric has a lot of cute cats. A lot of cute cats. But Odo has got the most neck floof, and I'm a neck floof kind of guy, so that's why I like Odo. All right, so the title of this talk is or was, Why Your Next or First Hardware Project Should Be Built with Nerves. So if I could get like a quick round of applause, how many people here have built a hardware project at least once before? Oh, wow. That's awesome. Now, let's get a round of applause. How many of you currently have a Raspberry Pi that's sitting in the box in your desk drawer that you bought at some point in the past with plans of doing something but haven't yet? Round of applause. All right. Cool. Actually, the disparity there was a lot lower than I thought it would be, so that's really cool. So here, I want to kind of give you a little encouragement, I guess, if you haven't started yet, or if it's been a while since the last time. So so as I said, the title is Why Your Next or First Hardware Project Should Be Built with Nerves, a walkthrough of building solutions with physical objects, comma, and how to do cool stuff. Okay. So before I get started, I do want to dedicate this talk to a friend of the Elixir community that can't be here today, Odo. All right. You kind of spoiled it, Justice, with the presentation, but this was in here as of yesterday. Okay, so who am I? I am Todd Resudek. I am a software engineer at a place called SimpleBet. SimpleBet is a software company that uses machine learning to build markets for the sports gaming industry. So we will make markets with software instead of with humans. So calculating odds for events that happen in sports games. And since we use machine learning, we can do it at the speed of almost at the speed of light. So you'll be able to bet on the outcome of every pitch of a baseball game, for instance. I'm also a member of the Hex core team, which I speak about often, probably too much by most people's standards. And you can find me online at Super Simple. So as I said, the goal for this talk is, first of all, to show you how easy embedded projects can actually be, and also just to encourage you to get started. So you might remember me from such embedded projects as the Drizzle 2000. So if you were here last year at Lonestar Elixir, I gave a talk about the Drizzle 2000, which is the future of sprinkler systems. And yeah, it's pretty awesome. And so, and this is a nerves-based project, of course. So, but today I have something very special to show you. Yes, and I'm calling it the Breathe X. All right, this is it. The most beautiful air quality monitor available today. It's simple yet powerful, and I think you're gonna love it. Okay, did you catch it? I was channeling my inner like Steve Jobs. There you go, Tim Apple, Steve Jobs, whatever. All right. So it was inspired by this device, which I didn't build. This is called the Aware. This is a desktop air quality monitor, and it costs $199. So I was actually looking to buy an air quality monitor for my house, and I saw this and thought, this is pretty. First of all, it's aesthetically very beautiful, but also does everything that I want it to do. But being the tinkerer that I am, I asked myself this question: can I build one of those? So a little bit about my background. I studied information systems at the University of Wisconsin. All right, nobody else from Wisconsin? Okay. All right, that's fine. I started my career as a designer. And then so far I have worked in web development for the last 17 years. So notice none of those things says formal education in electrical engineering. So when I start out to build these things, it's basically like this. So luckily, NERSC projects use very low voltage, so it's really hard to kill yourself. Not impossible, though. So be kind of careful. So my first step is, okay, well, this thing measures air quality, but what does that mean? Like, how do you actually measure air quality? How do you quantify the quality of air? And so these are some different sensors that measure air quality. So starting from the top is a particulate matter sensor. This one is the PM2.5. So that it has a little fan on it, an induction fan on it, and essentially just measures if there are larger particles in your air. So that's one way. The second one, which John Karstens loves, is the SGP30. And this one measures CO2. And so that's another way to measure. CO2 is usually good for if you're in a space with large crowds or an industrial space where there might be a device that's off-gassing CO2. CO2 will kill you. But the third way, this bottom one, is the BME 680, and this one measures volatile organic compounds. The easiest way to think about those are anything that's in the air that makes a smell. And so that's the one I decided to go with. The total cost of the parts for this project was $68. So much less than buying one yourself. And only like 250 hours of labor. So amortize that out, I save myself probably like, I don't know, negative $2,000. So a little bit about the BME 680. So once you get into nerves, you're going to start to like know all these little acronyms and little names like, oh, you have a DHT11, oh, I have a DHT22, or I have a BME 280, et cetera, et cetera. So they start to actually make sense to you, which may or may not be a good thing. But the BME 680, it measures temperature, humidity, barometric pressure, and VOCs. The sensor itself is actually that tiny silver square that's in the middle, about 2 millimeters square. The rest of this is just the circuitry to give it power and to communicate out. This one communicates via I2C or SPI. There are 4 really common protocols in embedded devices. These are 2 of them. I'll talk a little bit more about I2C later on. And this one costs $23. The next component was this Raspberry Pi 3 that you already have. So this one has a 1.4 gigahertz quad-core ARM processor. It's got a bunch of GPIO pins, and it costs about $35. You can get it less. Sometimes it's down as low as like $29. And lastly, or not lastly, second to lastly, which would be the penultimate, I guess, penultimate hardware item is the NeoPixel stick. This has 8 addressable RGB LEDs, and it costs about $6. Using LEDs, you can do it for less. Like single color LEDs are infinitesimally cheap. This was $6, but these are RGB lights, so you can change colors on them. It's got each one of those is a 24-bit color pixel. And lastly is a 5-volt fan. So this is important to get fresh air into the sensor. So you don't want to be measuring the same air over and over again. So in this case, you take the fan that's normally used for cooling, pulling air out, you turn it around, pull air in. And that forces air, as You might have guessed, and it cost about $3, $3.50. All right, so I got all these components. I tested out the fan by giving it a 5-volt source and realized this actually runs really, really fast. Rather than to have this extra noise and to have this much circulation for this small device, can I slow it down? And that led me into this deep well, which is called voltage dividers. So the speed of the fan is influenced or determined by the voltage that you give it. So it's designed to run at a certain number of RPM, given it has 5 volts. If you give it less voltage, it's going to run slower. So it's really important to remember all of this stuff is just physics. So it's not necessarily easy, but physics is very well documented and generally reliable. So this may be you as well. But so for voltage dividers, I don't know, for some reason this makes sense to me. Does this look like it makes sense to anybody? Yes? Okay. You're very smart people. So a voltage divider is just a passive linear circuit that produces an output voltage that is a fraction of its input. So in this case, that thing on the right is you've got voltage in, so that's 5 volts, let's say, and you've got a resistor, which is a really small device, and when you get involved with nerves, you have like 300 of them sitting around at any given time, and then at the bottom is a second resistor, and basically the ratio of those two, of the resistance of those two resistors determines what the fraction is going out. So if you put a 10K ohm resistor on both sides, then it's going to be half the voltage. If you need a different ratio, you just adjust the ratio of the top part and the bottom resistor. So I began playing around with different voltage resistors to find out what's the minimum voltage I can give this fan and have it still spin, which ended up around 3 volts. So that was interesting, I guess. So why use nerves for this? Certainly we've had embedded devices long before we've had nerves. All of the components that I showed you are supported by Arduino, for instance. You could definitely write this program in C. And so just to be clear, I think C is actually great. But for those who maybe are not familiar with C or it's been a while, this is a very contrived example of a C program. It's a procedural language, so keep that in mind. And the anatomy of this is, includes some basic stuff. Like in this case, I want standard I/O, so I've got to include the interface for that. If you're a Go programmer, this makes sense to you. You allocate memory for these lists or these arrays. So when you want to get a block of memory for an array, you have to kind of know how big this array is going to be at the beginning and define that. And then, of course, at the end of the program, when you're done with that array, you've got to free that memory up. Since there's no automatic memory management in C, you are the memory manager, and if you forget, you will run out of memory eventually. So when I picture C in my brain, I picture this. Anybody know who this is? Screaming out? What's that? Oh, man. Okay, so this is Derpy Hooves. She is a My Little Pony, if you have not guessed. Her real name is Muffins, and her cutie mark is not Muffins for some reason. I don't know why. So anyway, this is Derpy Hooves. She's kind of slow, and just like a C program, you have to give her very specific instructions on what to do. But at the end of the day, she is a Pegasus pony, so she can do a lot of cool stuff. Okay, I see my My Little Pony analogy just totally landed. That was awesome. We are definitely in trouble. Okay, so I think this application could have been written in C, but let me show you some of the code and explain why it would have been much harder to do it. So we have a to-do list. Like, what does this thing actually need to do? It needs to collect the sensor data. Then it needs to store the sensor data to a cloud service. So in this case, I'm uploading it to Google Cloud Data Store. And then it needs to display the current data. So let's take this step by step. So the first step is to take the measurements. And the first thing we do is set up this linked process to the sensor. So the BME 680 module, that's the air quality sensor. And so we start a linked process, and we give it that I2C address of 0x77. So that's opening the connection to the sensor. And then we start a timer and say every 10 seconds, go and collect some data. So next is the measurement module. So this is the recurring job that it runs every 10 seconds. So BME 680 measure the state. So it takes a measurement basically. Then it sends that to the measurement data, which is the local data store, sends that snapshot to that. And then what it does is starts an asynchronous task to send this out to Google Cloud. So since we're collecting this data every 10 seconds, that's about 8,600 data points every day. And rather than to run this synchronously, we run the potential that if it is blocking, maybe Google Cloud isn't responding, maybe it's down for maintenance, et cetera, et cetera. And in this case, we're taking 8,600 data points. If we miss 3 or 4 or 10 in any given day, it's really not that big of a deal. So we're just going to basically pass this along, assume that it happens, and if it fails, it's not going to crash the system. So this is the data module. So this is essentially where we're storing the current state. Pretty simple. This uses the agent abstraction, but at the end of the day, it's just an Elixir process that holds the sensor data. And then finally, we've got output. So we've collected the data, we've uploaded the data, we've stored the data locally, and now we need to output it to the display. So we start out with some baseline measurements. So in this case, the device lives in my home office, and so I collected a bunch of data to kind of see what the average is, average conditions are, and so that way the display will let me know when they are not average. So gas resistance, humidity, temperature, and pressure. So humidity and pressure, those are probably measurements that you're used to seeing. So it's in Celsius, and then humidity is measured as a percentage. The pressure is measured in hectopascals, which is a new one for me, but apparently in the metric system, that's very common. So normally we measure in inches of mercury in the US, so you'll see like 30 to 40 generally as a measurement. But in this case, hectopascals is a different measurement, and 801 is a livable condition on Earth. And so gas resistance is not volatile organic compounds. It's called gas resistance. And essentially what it's doing, that sensor is doing, is measuring how much resistance exists in the air. And that's what determines the impurities. So that's why that's called gas resistance. And so this is the output module. So every 10 seconds it draws a frame. So drawing a frame basically means like change the lights or the state of the lights on the display. And so it does that, calculates the relative values, and then writes it out to the display, which looks like this. Basically just says, here's my measurement. How does that relate to what I know as a baseline measurement? And then give me a value from that. So in hardware, we have very defined restrictions on how we can display data. Our interfaces are generally very simple. They're limited by the hardware we have, physical limitations, like a switch can't be that much smaller than the size of a human finger. A light has to be large enough that you can actually observe it with your own eyes. So if we're as web developers, we don't have those same constraints. So we can build interfaces like this, where, but this is not something that you can really build in the hardware world. In hardware design, we have to think about all of those constraints and work within those limitations. So I kind of wanted to explore that. I have a lot of data, as we saw, and how am I going to output that to a user with the equipment that I have, with the form factor of the air quality sensor, in a way that somebody could glance at it and make sense out of it. So there's a few ways that we can output things more simply. So here, instead of the previous image with a lot of pixels, we can limit ourselves in the dimensions of the space and have a low resolution image. In this case, it's in 2 dimensions, so we've got an X and Y coordinate. We could add a 3rd dimension to this, which is time. So that's, think about that. We have really 3 dimensions to work with in this case. But this is also, the hardware required to do this is more complicated than what I have. So another way to display these metrics is on a single dimension. So if you look at these 8 lights, which represent that NeoPixel stick that I showed earlier, you can think of it as a single dimension, a very simple meter where the amount of lights changes as the measurements go up and down, like a simple VU meter. And if you add a 3rd dimension to that, this looks like one of those old graphic equalizers, for instance, from your music player. So now you've got both the X coordinates and the Y coordinates can change. So now we've got a 2nd dimension. But going back to the single dimension, we can add a dimension of brightness to it. So instead of a Y coordinate, we have just the X coordinate, and we can use relative brightness of the lights, and that could be meaningful. In this case, we take a single light, and we could change its color and give those colors different meanings. And that's really what I ended up with. So just to show you the display again, so I think humans are used to the normal rainbow of red being on one end of the spectrum and violet being on the other, and kind of knowing that those oppose each other, and are generally familiar with all the colors that come in between. And so that's where I ended up for the display of this. So white being the baseline measurement. As the colors get colder, that means the measurement is going down. As the colors get warmer, that means the measurement is going up. I have got the Breathe X with me, and the cord's not very long, but you can kind of see it's a rainbow right now. And so your leftmost measurement is the temperature, followed by humidity, then pressure, and then VOCs. So you can see the VOCs are a very bright red, which is not a very good sign for us. Yeah, so is everybody still alive? Anybody dead? If you're dead, raise your hand. Oh, crap, Zach died. Okay. Yeah, so those were the constraints that I worked in for the display. And here's a in-code version of that. So this is artificial intelligence, everybody. You can see it's got 7 function heads, so that's amazing. So, yeah, if we're basically if we're 50% below normal, we're violet. If we're 50% above normal, we're red, and all the colors in between. So, but one of the nice things about working in the Elixir ecosystem is that we can also code all this up in Phoenix. So this is an interface that I built to get a better glance over time of the data. So you can see this live view graph at the bottom represents those measurements, and then I've got these donut graphs. So this is me breathing on the sensor. That's what that big spike is. And I would say, considering I used to work at Weedmaps, that's not too bad. And a lot of people have asked me, how do you make these graphs in live view? And it's actually a lot simpler than it looks. So this just uses regular SVGs, and you can see the points there. I'm just feeding in my data to that points attribute, and it will make those very pretty graphs. The points data looks like this. So it's very readable, obviously. But these are just XY coordinates relative to one position on that graph, so the top left position. And so it's a pretty simple calculation. You can make yourself a Phoenix front end for this as well. All right, so back to nerves. So another reason to use nerves on this is the concurrency model. So if you remember, we had all these things that we needed to do. So why not use this quad core magic and do them all at the same time? So even an inexpensive device like the Raspberry Pi has got 4 cores on it. So you've got 4 schedulers able to handle all those tasks. By contrast, this was my first computer. It is not quad-core magic. This is a 60 megahertz single-core RISC processor with 72 megabytes of RAM, which I assure you was very impressive at the time. Another reason to use nerves is the stability. So you're probably familiar with these supervision trees, and this is the one that I have mapped out for this application. So if you look at it, I've got these trees that are managing the cloud service, independent of all the initialization of the network and the display, which is also independent of the output data. And so, you know, like I said before, if the cloud service were to crash for some reason, getting some unexpected state, we are still collecting data and we're still outputting data locally all the time. So in fact, the device that I have here today is not set up for the Wi-Fi connection at the conference here, and so this thing has not been able to make a connection to the cloud supervisor all the entire time we've been here, yet it keeps running. So I think of the Erlang processes like this Pinkie Pie here. So she's juggling these boneless chickens just like Erlang is juggling all these processes. And in this case, she's standing on a ball at the same time. All right, so what if your program does this? All right, this guy died, by the way. So an IoT, okay, he didn't die. Well, he might have died. I don't know if he died. All right, so what if we crash? What if we've got a power loss? What if we have network inconsistencies? Am I going to brick this thing? No, no problem. So there's some behind-the-scenes features of Nerves that can really help you out. So Nerves can alternate its boot partitions. I know Justin talked a little bit about this yesterday. But essentially, you've got 2 boot partitions. So you're loading your firmware to one of these 2 places, and you alternate them. So if you try to load new firmware to position A, and it is broken, doesn't compile, etc., or that you lose network while you're pushing that, you will always have a very clean version of the firmware on the other partition to fall back to. So it is, in that way, it's very hard to brick your device. And also flexibility. So if you are, all right. So if you're building with Nerves, as with anything in the Erlang ecosystem, you can use ports to bring over, C programs, Python programs, Rust programs into your system. So it's very easy to be very flexible with your code in the Nerves ecosystem. And last but not least is the community. We've built a really great, passionate community in Elixir, and the Nerves community is no different. We're a small group of mostly hobbyists. Some people come from backgrounds in electrical engineering, but most of us don't. We're just programmers that have an interest in physical things. And so we've got all these libraries that help us make these things very easy. So for Bluetooth or video or NeoPixels, Z-Wave, etc., we've got these libraries like Grizzly and Scenic and Herald and Elixir Circuits and BlinkChain that can make these working with these systems very, very easy. So in addition, we've got a remote meetup group. We meet every month. So you go to the website nerves.group, and it's 1 hour a month. We get together online and just chat about projects that we're working on and help each other out with problems that we're having, and generally just encourage each other to finish the projects that we've started. And as I understand, there's also a meetup group forming, or maybe just formed in Japan. So konnichiwa. We also have a Slack channel. We've got over 2,000 members to the Slack channel. Great place to ask questions. So I would say in conclusion, come join us. It's easier than you think, and it's actually a lot of fun. The hardest part of a Nerves project to me is learning Elixir. So if you've already learned Elixir, you've overcome one of the major hurdles. And for the rest of it, we've got people here that can help you. So you don't have to be an electrical engineer. You can just act like you know what you're doing, and we'll help you figure it out. All right, so first, just thank Maggie. I want to thank Maggie and Bruce Tate for inviting me to speak at Lonestar Elixir, and thank all of you.